we're going to be able to calculate and predict whether or not a reaction is at equilibrium at any time. Okay, at any time in a reaction, you can just basically take a snapshot, measure concentrations, throw them into this expression, and calculate a value. Now that we know what an equilibrium constant is, we're going to be able to calculate and predict whether or not a reaction is at equilibrium. And so what we're going to use is something very similar called a reaction quotient. Now remember, these KCs, we plug in concentrations at equilibrium to calculate a number for that. We're going to compare it to a reaction quotient, and this is really simple. So a reaction quotient, we're going to use the same expression as your KC. So remember, products on the top and reactants on the bottom. The product of those concentrations. So we'll calculate a value, and then if we have the Q that we calculate is equal to KC, we will say, hey, we are at equilibrium. Because remember, when you're at equilibrium, you plug in those concentrations and you calculate KC. All right, so what if we are not at equilibrium? Let's say we have calculate the Q and it is less than KC. Well, remember what is on top. So we have too much product. We have products on the top, and then we've got reactants on the bottom. I'm sorry, that would be the opposite direction. We would have a big reactant, right? We have a large denominator, and then we have a small amount of product. So if Q was really, really small, we would have more reactant than we need, than at equilibrium. And what's going to happen? That reactant is going to shift and produce more product. And so this thing will shift toward the product side, and it will come to equilibrium. Similarly, if we had a Q that was greater than KC, we would have too much product and not enough reactant. And so this reaction would do the opposite. It would swing back toward the reactant side or back toward the left. So let's look at an example, and I'll show you what I mean. Here's a reaction. I've got 3 gases here, and I've already written the expression. So this expression here for Q is exactly the same as KC, okay? And then we're given some concentrations. I've got the concentration of water, hydrogen, and carbon monoxide. So that's what we did. At some time, we are throwing in our concentrations. So on the top, I've got O2O molar, and then the other one is O2 molar again, and then the water is 1.5 molar. Okay, well, we crunch the numbers, and we're going to get, for Q, we're going to get 2.7 times 10 to the minus 4th. That's Q, okay, at this time. Now, that's meaningless unless we compare it to KC. So we look up KC at the same temperature, and we find this value. Well, when we compare, we notice that Q is less than KC. So what does that mean? If Q is too small, I don't have enough product, right? My numerator is too small. So the reaction will proceed to equilibrium, and to do that, some of that reactant, water, will convert into product, okay? And so the reaction is going to shift to the right or toward the product. And that is how you calculate Q and determine whether or not you're at equilibrium, and then which way the reaction will shift to get to equilibrium.